Alex is someone who I've known for a long time now. He's one of the co-organizers of Zurihack. He's also a co-organizer of the NICS hackathons that also happen here twice a year, right? In case you're interested, please, there'll be a QR code for that. And he's also one of the co-organizers with me for NICSCon that happened in 2025. So yeah, it's really great that there are many extra people here. And thank you very much, Alex, for agreeing to do this guest lecture.
All right, let's see if this works. Yeah? Okay. Now it's there. So thank you very much, Farhad, for inviting me. It's popping a little, isn't it? Yeah. Now it should be fine. Yes, thank you very much for inviting me. Thank you very much all for joining me today to hear about a topic that I'm actually very fond of. NICS is a technology that I've been enjoying in the industry for the past 10 years or so. I've also been working in functional programming. I'm currently working for a small startup here in Zurich that uses functional programming and NICS. So if you need a job in functional programming, come talk to me during the break or after the lecture. So I've structured this lecture into two halves. We have 2 hours. The first half will be more theoretical foundations of how NICS works, what it is. And then after the break, we will look at some of the cool things you can do with it, how it can solve your problems. Because this is a university, the topic is an academic one, or rather has roots in academia. There are some publications that you can read up on if you're interested in more in-depth knowledge. All of these lectures are online. There was a link at the beginning, maybe I can show that again, on GitHub. So if you want to follow along or read it after, you can access it there. Farhad will also upload the PDF. Okay, so let's have a show of hands. Who here has ever heard of NICS? Wow, quite a few people. Okay, does anyone here use NICS? Fewer, very good. So don't worry if you've never heard of it or if you've never used of it. In fact, it's probably better if you haven't. I find that it's easier to tell people about NICS when they haven't learned about it yet. And the reason for that is that everyone learns NICS in a different way. Everyone learns a different subset. Different people use NICS for different things. And the way people learn about NICS, the way they hear about it the first time and start using it is because someone comes to them and sells it to them, like a used car. And in fact, here we are in this lecture hall, and I'm here to sell you NICS. So why is that so? Why am I here to sell you NICS? Because I believe that NICS solves a problem that everyone here has, a problem in software engineering. And even if not all of NICS topics or solutions are relevant to you, it's still a very relevant and transferable skill. It's not a single tool, it's not a single technology, it's a research field of sorts, an active research field, and it will shape the future of software development. So if we learn about it here, you can continue applying it in the future. So NICS was invented or brought to light in 2006 by a Dutch fellow by the name of Elko Dolstra. He wrote a PhD thesis titled Functional Software Deployment Model. And he described NICS as follows. NICS is a solution for getting computer programs from one machine to another. So what's the big deal about that? Computer programs are just some files, and surely copying files from one computer to the other is a solved problem. We can use a USB key or the internet. So copying is not the hard part. We have this, for some reason, we've decided that these programs should also still work after we've copied them. And this is an interesting and difficult problem for, in my opinion, 3 reasons. One, there's more and more computers in the world. And these computers are more and more different from each other. Despite our best attempts at standardization, there's various shapes and sizes, various architectures, various operating systems that don't understand each other. And lastly, the programs that we write and want to run on these computers are increasingly complex. We want to do more and more with software. So we can't really change the direction we're going. We can't reduce the number of computers or the number of the amount of diversity, but we can think about what makes computer programs complex. Why is it that they're increasingly complex? And the reason is that software is increasingly written in a way that we reuse components. We have a set of files, but we reuse these files between projects. we build on top of the shoulders of giants, and these are called dependencies. Dependencies such as compilers or libraries. Show of hands, who has in the last year installed a compiler onto their computer to build some software with? Okay, a few, all right. Who here has had to collaborate on software with another person on building software? Okay, a few, yeah. Okay, and finally, who ran into issues doing either of these things? Who had any issue at all? Okay, a few. All right, well, those of you who did not raise your hands, you either don't write software, which good for you, or you write software in an ecosystem that solves these problems nicely for you. And truly, enjoy that as long as it lasts. For the rest of us, these problems are not yet solved, at least not in the general case. What is the problem exactly? As the software author, you have the compiler and the libraries and so on installed on your computer, because otherwise you couldn't build. However, the people that you want to share your software with, be it your collaborators or your users, probably will not have these dependencies installed. A compiler, yes, perhaps, but with libraries and the configuration files and so on, we cannot assume. Especially with users, we can't really assume anything about their computer, their operating system, or whatsoever. So the question becomes, how do we ensure that other people have these dependencies installed? As software authors, presumably, we've written this software to share with other people, so we want to make it as easy as possible for other people to use our software. And a common way to do this, at least in the open source, is to write documentation, or README files, which count for documentation. The problem with documentation is that it takes effort. You have to write English or whatever language, and actually sit down and do it. There is no guarantee that this documentation is complete or correct or up to date, if it's there at all. I famously don't write any READMEs. So even if you find some documentation, it might not be applicable to you, it might not work, right? So as a software author, at the very least, we should specify what we expect from the other person's computer, or to be on other person's computer. But because we want to help other people install their software, these outdated ways of documenting dependencies hurt the user, not yourself. The author doesn't feel the pain because he already has all of the dependencies installed, but the users feel the pain when they try to use it, it doesn't work. So as the software author, you want to help the user as much as possible, and as software engineers, the best way to test that something works is to write a program that tests this for us, that we continuously test our specification. So ideally, the specification of our dependencies, of our expectations, is a program that we can test, right? So Linux users, rejoice, already use a form of this specification, let's say, called a package manager. An example of a package manager on Ubuntu would be Aptitude, RPM on Fedora. There's Flatpak, which is kind of cross-distribution. Mac users have Homebrew. Windows users have something called Chocolatey these days. So these programs specify dependencies for a piece of software so that you can install it with a single command. However, even if two users use the same package manager, like let's forget about the fact that there's multiple, even if you use the same package manager on two different computers, you might have access to different sets of software or different versions. Just because we both use Ubuntu, maybe you have a different version of a compiler than I do, and then my project doesn't build anymore. Another big problem with classical package managers is that as you update your system, as you bump versions of dependencies, programs, and whatnot, the old versions are deleted and replaced. For example, if you had Blender on your computer and then you ran an update, Blender 4 was replaced with Blender 5. Maybe Blender 5 introduced some new features that you don't like or removed some features that you depended on. And the question becomes, how do you get that back? How do you recover from a situation where an update removed some things that you wanted? Maybe it completely broke your computer. Maybe it doesn't boot anymore. This is a pretty common situation for Arch users. How do you go back to a working state? With a classical package manager, not so easily. Another problem, as I mentioned, Blender, right? What about if you have two projects and one of them depends on a newer version, one of them depends on an older version? With a classical Linux package manager, you would have Blender in /bin/blender. And which version is that, 4 or 5? Maybe there's a Blender 4 and Blender 5, but it's not a general rule. So, in the world of software deployment, there exists a solution. It's called Podman, or Docker, I guess is the one everyone knows. Podman is like a modern new implementation that everyone should switch to. This is generally called the OCI, Open Container Initiative. And these are, the way Docker works is that you share a binary snapshot of a file system between computers. The problem with these binary snapshots is that it's a blob, it's a bunch of bytes. You have no idea what these bytes contain. You can look at them, but you have no idea where they came from, who built them. Usually, these blobs are paired with a recipe or a Docker file, but there's no guarantee that this recipe produced this binary blob. Maybe there was something in between, some kind of tampering with the files that you can't detect. However, even if you use this recipe and build your own binary blob, your own snapshot, there's no guarantee that this recipe is complete or correct. You can take a binary, put it into a Docker image, then install some of its dependencies, but not all, and then only when you try to deploy this to production and run it, will you discover that there are missing dependencies, and then you have to redo the whole process again. It gets worse. Even if you have a recipe, a Docker file, that works at the moment, you've tested it, you produce an image, it runs. If you build the same Docker file tomorrow, you will get potentially different versions. There's no guarantee that if you build it twice, even on the same day, that the contents will be the same. In fact, if you're using something like Ubuntu, traditionally you would use a package manager inside of your Docker file to install some dependencies. If you're using something like Ubuntu, some versions might have bumped and so on. So then you have to rerun all the tests and do the whole thing over and over again. It's repeatable but not reproducible. I could go on about this all day, but let's talk about Nix, not Docker. By the way, if there are any questions or comments or criticism at any point, just raise your hand and I'll answer them. We also have a live stream, so if anyone on the live stream has questions, I can also answer those in real time. Okay, so to recap, what do we want in a solution for copying programs between computers? We want something that's reproducible, not repeatable. So if it works on one computer, it should work on another computer, regardless of operating system or versions or whatsoever. And if we had something working yesterday, like this lecture, for example, last year, it should still work this year. It should be declarative rather than imperative. What this means is that we can specify dependencies in a way that don't interfere with each other, and they can be composed like functions in a programming language. We'll see more about this later. And lastly, reliability. So we have the ability to roll back if something breaks, and as I mentioned, there's no interference. Like if you add another package, it doesn't break other packages. So I mentioned completeness and correctness. We want to know that what we've declared as dependencies actually makes our software work. How do we make sure, how do we test that our declaration is in fact correct? Well, we run it in a sandbox. It's an environment in which we don't give access to any resources that are not declared. So for example, if we say that our program needs SSL as a dependency, but we forgot to say that it also needs some compression library or whatever, then the specification should fail because it can't access the compression library because it wasn't declared. Importantly, this means there's no access to the network. We can't just download from some HTTP resource because, again, those can disappear tomorrow. Or hardware for that matter. We can't read from disk or in an uncontrolled way because what's there on the disk today may not be there tomorrow. Okay, that's kind of a brief overview. Another thing I would like to clear up is that, as I mentioned, Nix is not one thing, it's an ecosystem, and something that trips up beginners when they start looking into it often is that things are named a little confusingly. There are several things that are named Nix. They all have this nice little snowflake, but they're named very similarly. So there is the Nix, which is the package manager, the program that you install on your computer and run. And this program accepts programs written in a language, which is also called Nix. Usually I just call it the Nix language. There exists a software repository called Nix packages. It's on GitHub. That's the largest software repository for Nix programs. And there is also a Linux distribution built on top of Nix called NixOS. Contrary to popular belief, you can use Nix without installing NixOS. You don't have to change your operating system. It works on all flavors of Linux. It works on macOS, and it works on Windows in WSL. OK, you still with me? All right. To understand how Nix works, we have to talk about one central concept, and that is the Nix store. And to illustrate what the Nix store is, let's draw a parallel with computer memory. You've all done some software engineering courses by now. In computer memory, we have a stack and a heap. Heap is where the allocated objects go, right? So we're going to talk about heap memory. So the Nix store is a file system tree. In other words, a folder on your disk. And let's imagine that this folder is a heap of a computer program. Into this heap, we can allocate variables, arrays, objects, whatnot. In the Nix world, these are called store objects. They're in a file system, they're either files or directories. But in memory, they would be allocated objects. Allocated objects in memory have a pointer, an address, right? And in a file system, this address is basically the path to the file or directory inside of the Nix store. So in practice, it looks a bit like this. It usually starts with /nix/store. This is the Linux file system kind of way of encoding paths. There's this long hash, and then -hello is the name of the object. And we can, of course, access files through these paths, and files can also contain these pointers, these paths, to refer to each other. So we can have some kind of dependencies between objects. You would do the same thing in a linked list, for example, right? Each object in a linked list has a pointer to the next object, or previous, depending on how you implemented it. So here's a funny question. If this Nix store is a heap memory of a program, what is this program? Which program uses the Nix store to populate it and use the things that are inside? Well, if we think about, or if we look at the shape of the Nix store, we can see some of the properties of the program that populates the Nix store. We know that it's a functional program. So it's a program written in a functional language. What does that mean? That the basic building block of this program is a function. We constantly, it's functions all the way down. We just compose functions, we write functions. These functions can have multiple inputs, but they always have one output. And if you call the function with the same inputs, it will produce the same output. That's important. That means that these functions are referentially transparent. If you add 1 plus 2, it doesn't do a DNS lookup, it just returns 3. So remember, the Nix store is heap memory, and all of the objects in the Nix store are kind of variables and pointers and so on, which means that the inputs and outputs of this function are also objects in the Nix store. You can't feed a function a variable that isn't in memory, right? Even if it's something on disk, you have to read it to memory first and then pass it in. Similarly, the inputs and outputs of this quasi-functional program are all store objects. So where the analogy breaks a little bit is that the Nix store is append only, which means that we can only create stuff. We can't really delete it. At least this program can't delete stuff. We can only create. So if you've done any functional programming before, this might not look too surprising. We combine a function with its parameter to obtain a promise. This is what in a lazily evaluated language, we get something called a thunk. It might be a Haskellism, I'm not entirely sure.
Yeah, it's like thinking, but in the past tense.
Yeah, the function has thunk. It's a promise that if we resolve this promise, if we cache it in, we get the result value. So this is the functional world. This is not Nix. In Nix, things look exactly the same. The function is replaced with build instructions. The parameters to the function are so-called inputs. If you think about it in this way, the build instructions are themselves an input. And similarly, in a functional programming language, the function is also sort of an input to the thunk. The thunk has become a build task, which when realized, when we actually perform it, we don't have to. But if we perform it, we get a build result, which can be some files or whatever. Okay? So in in functional programming, we can compose these functions, right? We can call a function with the output of other functions. I know that this graph probably looks a bit confusing, but inside these boxes are just more functions, right? It's functions all the way down. So the outputs of one function can be inputs of another function. The same is true in Nix. So we can write a function, some build instructions that reference the outputs of some other build instructions. And in this way, we've built a pipeline, right? So pop quiz time. If all of the things in memory in the Nix store are created by this program, are outputs of these build results, how do we get the leaves of this tree? It's a DAG, right? It's a directed acyclic graph. How are the leaves of this graph? Who created them? How do they get in? If a function can only take inputs which are themselves store objects, where do those store objects come from? And if they themselves are outputs of another function that created store objects, where do its inputs come in? Right? How do we populate the initial values? It turns out that Nix allows us to copy a file that already exists on your disk and put it verbatim into the store as its own, as a leaf, right? Okay, so we know how to create constants. Let's see how we can create functions. A function in Nix really is a Unix process, so or just a computer process, really. But we carefully choreograph it such that it behaves like a pure function. So again, what does it mean that it's a pure function? That it can't read anywhere but from what we explicitly allow it to read, so the inputs, right? It can't read the disk, it can't read the internet. It can only write to where we want it to write, so that's the output. It can't create side channels, it can't have files all over the place. And the output of this program, as I mentioned, will itself become a new store object. So it can't write into, well, I suppose it can write into the temporary directory, but that's temporary. But anything that it wants to persist has to end up in the Nix store. And these functions, when they obey these laws, when Nix choreographs them, they're called derivations. Out of the old, we derive the new. And derivations themselves, so the kind of the specification of this function, remember, to create a func, the function is also an input to it. And inputs are store objects, which means that the functions themselves are store objects, which means they're files. We'll see very quickly what that means. This is a file in the Nix store. It's represented here as JSON. The real representation of this file is some binary format that no one understands. But represented as JSON, it has everything we need to derive or cook up some new files in the Nix store. Let's have a look. We have the builder. That's the Unix. I mentioned there's a Unix process that will run, right? That's the builder. And if we look at the end of the builder, it's SH. SH is the Unix standard, the POSIX shell. The shell can be then called with these arguments, which are also specified. These are the inputs of sorts. And we say -c, which means run the following string. And we have this echo hello redirected to out. If you've written any bash, you can probably guess what this does. It writes the string hello. $out is an environment variable. I omitted the specification of the environment here, but there is an environment variable called out, which is actually this path, which gets computed in this outputs object. So Nix has computed the hash of an output path where our process can write. And into this path, our hello will be written. So this path, after we resolve this promise, force this func, will contain a file with the contents hello. And we also have a specification on which system this runs. So bash happens to work also on other systems, but maybe we have some Linux, either Linux specific or x86 specific program, and we say here that this can only run on a certain architecture. We also see here we have these input sources. So remember what I said, the process can only read what is specified as an input source. So the builder, the process that will run, has to be an input, otherwise it can't run. Make sense? Okay.
So one thing here, who has generated this file?
So the question is, where did this file come from? Very good question. Remember what I said earlier. Anything in the Nix store there's only two ways to populate the Nix store. Either a previous function has run and created this file, or we copied it into the Nix store as a verbatim object. So both of these are possible. We will see examples of both. You can write these by hand. So you can open a file, write this function in. You can ensure that the shell binary has been copied to the Nix store manually by you. And then you can reference it like this. And from this, so basically you copy in the shell binary, you create this very verbose file by hand. You make sure that the hashes all match. And then you can copy this file to the Nix store, and then you can execute it in a way that we'll see later. That is a very laborious process, which is why there exists a language called the Nix language.
Another quick question. There's only one Nix store per system.
There is only one Nix store per system. Yes. And in fact, this Nix store is always in /nix/store, even on Darwin. There is work underway to make it relocatable. I'm not entirely sure how far along that is. What's more interesting is there can be one Nix store for multiple systems if you mount it as a network mount or so on. But that's also an ongoing area of research.
So this is basically the heap that we're talking about with the analogy of functional program. This would be the heap.
Well, what we're looking at here is a function that exists as a file in the Nix store. So in a sense, it's in a functional programming, this function would be a memory region with a pointer to it, right? In this case, we see the pointer up here on top. It's this hello.drv. So that's the memory address of this function. It is itself an object in the heap memory. Just as in functional languages, if they're compiled, they will be placed into memory, right?
So the store is not this file, the store is this plus the file system.
The store is a directory containing this file and many more. It will, at the beginning, it probably contains nothing. Then we manually have to copy in the sh binary. We have created one file in the Nix store. Then we have to manually copy in this drv file. Now we have two files, sh and drv. And with these two files, the rest of this file works. Because it references only sh, and it will create a new output. So after we execute this, we will have three files in the Nix store. sh, the derivation, and the output of the derivation, which is this out.
Got it. So this is sort of like the table of contents for this directory. What's there?
The table, no, this is only one derivation. This doesn't describe the whole Nix store, yes. Only a few files. It's a recipe.
Got
yeah,
it.
just like a recipe doesn't describe your full kitchen, it describes what's needed to make something.
Okay, cool.
And as I mentioned, if we rerun this multiple times, if we execute the same build multiple times, we are not actually creating new objects because the hash does not change. So we're not even overwriting it. Nix will check that the output already exists and then say, success, I'm done. Just like with a recipe, right? If you try to create a cake twice, you might notice the second time you already have cake and declare success. Okay, let's talk about the Nix language. So we've seen this ugly JSON that you have to write by hand. Surely there's a better way, right? First of all, why do we need a language? Well, as I just said, writing these derivations is very error-prone, laborious, and we can automate it by using a language that generates these files for us. And that's what the Nix language does. So here's, again, the beautiful JSON. And here's the Nix language, the equivalent Nix language expression that generates the derivation on the left. Yes, question?
You haven't answered the full question you posed. Why do we need a new language? What's on the side?
Yeah, there is a separate slide where I explain that Nix is a domain-specific language, and then the question is, why is it a domain-specific language and not a general-purpose language? I guess that's the answer, because we don't want a general-purpose language. We want a domain-specific language. It also has some unique features. But you are right. I guess the question isn't really fully answered.
Could I ask one more thing? So this JSON, where can I find it in my Nix store?
Okay, so the question is this JSON on the left, where can we find it? Well, on top, there's a path to it. Every time when we execute a Nix build, such a it's not really a JSON, it's a derivation file which has its own syntax, but such a file will be placed in the store. And we can, with certain flags through the Nix process, we can see these files, we can inspect them. So normally, you don't interact with these files, you interact with the Nix language, which is this derivation block on the right. So this, when we evaluate this block, the derivation file will be created for us. We can inspect it then after the fact. We can evaluate, then inspect, and then run if we want to. And this is actually a pretty common workflow when you're doing some really crazy Nix stuff. But yes, so the answer is the Nix evaluator. The evaluator of the Nix language will create these files.
And I can have more than one of these hello. I can have a hello1.drb just after this also, so I can have multiple of these derivations inside this one file.
So the question is if we can have multiple derivations in a single file. No, I don't think so. This is just the representation. The reason it's a key value, the reason it's an object, is just for convenience so that you see the name of the file. But I think a single derivation file only has one derivation. Because if nothing else, they get different hashes, right? So if we evaluate the Nix language that's on the right, we get this big complex JSON on the left. Okay, so the Nix language is a new, totally different language from what most people are used to, and it's frequently let's say, an obstacle to people learning Nix. I will give you the very, very briefest of overviews of some of its features. Commonly, people say it's just JSON with functions, which is a little bit of an understatement. So let's just have a look at how Nix looks, the language. But that's really not the point to learning about Nix, so we'll not spend too much effort on it. So as I mentioned, it's a domain-specific language, not a general-purpose language. It is a purely functional language. So if you have used, for example, Haskell, or I guess OCaml isn't purely functional, but yeah, if you've used a functional language before, it won't look too foreign. It is lazily evaluated, which I guess really just leaves Haskell of all the popular languages, which means that as we write these expressions, we don't necessarily immediately get their results. We reference them later. It is a dynamically typed language, unlike Haskell, so more like Python or JavaScript, which means that values are only assigned types at runtime. Okay, so I mentioned values, and we can give values names. So integers, for example, we can have a let binding that gives some variable name a the integer 1, and then b is a plus 1. Who can guess what that is? It's 2. And then on the bottom, we say a plus b, so that it's let in, right? And this will hopefully evaluate to 3. I don't have the result on the slide, so I have to guess. We have attribute sets, which are kind of like objects in JSON or in JavaScript with these curly braces. It's just a little bit different from JSON because we don't put quotes around variables or around keys. So in this case, we are declaring an attribute set, an object, with a key value x1. So this expression below, attrset.x, will resolve to 1, or evaluate to 1. We also have strings, of course. So we can give the string a name. And we have string interpolation with these $signs. We'll talk more about string interpolation later. So in this case, the expression will evaluate to hello Nix. I mentioned it's JSON with functions, so we have functions. If you've written any Python before, you know that the lambda syntax in Python is the keyword lambda, then the parameters that the lambda captures, followed by a doppelpunkt, colon, and the implementation of the function. Here it's the same, just the word lambda is omitted. So it's f is a function that takes one parameter called x, and then returns x added plus 1, basically. So f given 5 will return 6. We can have multiple parameters. I guess this is a bit different from Python, but it's more similar to Haskell. Each parameter is given as a separate kind of parameter block. So in a sense, f is a function of 2 parameters, and if we give it x, we return a function of 1 parameter, and then if we give it the second parameter, we get the value, in this case 2 plus 3. Question?
No remark for those who had functional programming here. This is what you've learned to know as currying.
Right, yes. So the functions of multiple parameters are implemented using currying. So each parameter returns a closure over that parameter. Yeah. And in fact, you can use this with some, like this is used quite a lot in the Nix code bases. So it's important to understand it. We can also completely avoid currying by passing, instead of each parameter separately, we can pass in objects of parameters. This is kind of a more, let's say, C-like syntax, where we take an object containing certain keys, in this case a, b, and then return a plus b. And then when we call the function, we have to supply this object with like inline values. So this function, f, a, b, a plus b, is the same as the one that takes two parameters, just in object form or attribute set form. Okay, so as I mentioned, it's a language in which we can do functional programming. Here's an example of the famous Fibonacci, the inefficient implementation of the Fibonacci sequence. We have a function called fib, which takes a single parameter I. We have flow control with if, else, if, and else. There's no elif. We have double equals for equality, nothing particularly interesting there. So we can return, we have the edge cases of the recursion for when I is 0 or when I is 1. In the other cases, we just recurse back into fib. So recursion is natural. We have the map function, which is for some reason hidden in this built-ins, a magical construct. And if we call this function fib on these indices from 1 to 10, we get the first 11 Fibonacci numbers. Okay, any questions so far? Everyone's an expert in functional programming. Excellent. Okay, so forget about Fibonacci. The reason Nix exists, the language, is to create those derivation files that I showed you earlier, right? So what exactly makes Nix the language so appropriate, so good at building these Nix derivations as opposed to something else like Python or JavaScript? It has first-class file system paths. What that means is that in the Nix language, we can give a path to a file system object, let's say /bin/bash or something like this. And the Nix evaluator will take this file and put it into the Nix store for us and replace it with its store path. This is very important, very cool. It means that we don't have to put it into the store manually, get the pointer to it, and then put it in our program. We can just reference a file on the disk. It has string templating, which I already showed you earlier with these $ and curly braces. This allows us to write any language, any other language into a Nix string. For example, because we also have multi-line strings, right? We can write Python into a Nix string and then run the Python interpreter as the Unix process of a derivation, and then the Python program inside of Nix becomes its argument, right? And importantly, these interpolations can themselves be Nix builds, Nix objects. So for example, if we have a Nix function that produces some store object, we can interpolate it into a string using those curly braces. And we get something called a string with context. So that's the third very important Nix feature. A string in the Nix language is not just a sequence of characters. It's also a set of its dependencies. So if the string references a Nix store object, then anything that uses this string has those store objects as its dependency. It kind of bubbles up. If a Nix string is a parameter to a process inside of a derivation, then all of the things referenced in that Nix string will automatically become the input sources of that derivation. Whew. Does that make sense? So if we reference dependencies in the string, Nix automatically makes those dependencies kind of the dependencies of the program that we're building. Question?
Quick question. So what exactly is the derivation file? If you go a few slides back, what is, yes, that.
Yep.
Yeah. Is that the derivation file? What is that the derivation?
So the question is, which of these two things is the derivation file? It's a good question. The thing on the right is a Nix file, a Nix expression, stored probably in a .nix file, although we can also write it manually into the REPL. It doesn't have a particular name, it's just a Nix program. When this file is evaluated, then the evaluator will create a derivation file, which is the thing on the left, into the Nix store. The Nix file does not have to be in the Nix store. If we, in fact, usually it's not. If we use flakes, then sometimes they get copied over, but that's just an implementation detail. The point is that Nix programs don't have to be in the Nix store because they resolve to derivation files which are in the Nix store, and then those get fed as inputs to the thunks, right? So the Nix programs produce derivations.
That is the Nix program that produced this derivation.
Correct. In fact, that is exactly the Nix program that produced exactly this derivation. The only thing I omitted on the left was the environment to save some space on the slide.
A very pedantic question. How that hash was generated, but there's like a chicken and egg problem somehow in my head, right? So you need this derivation to produce the hash.
So the question is, where do the hashes come from?
Yeah.
The output hash of a derivation is the hash of all of its inputs. It's input hashing. So for example, we only have one input, and that is the runner, or the builder of our program, which in this case happens to be the shell. Let's just say bash, right? If we hash the bash binary file, we get a hash that corresponds to the contents, like to the bytes in that file, right? So if we use the same bash over and over again, it will always have the same hash. Then if we take the hash of this input as well as of the arguments, then we get a hash that is stable as long as the runner and its inputs or arguments are the same. So if we run this exact binary of bash with those exact arguments again and again, the output hash will be, even if we recompute it, it will always be computed the same way. And all of these hashes, so okay, the SH hash was created by Nix on the line builder equals bash. So remember what I said. In fact, I think if we just go forward one slide, yeah, I actually have the same thing here. So yeah, let's study what are the things that Nix did for us, right, in this step. So for starters, the input, the runner, the builder is an input, right? In the Nix program, we just say /bash. Remember, it has to come from somewhere. Bash isn't just created for us with the Nix store. So assuming that you have a bash binary that works sitting on your disk, it has to be statically built, right? Because the dynamic dependencies are not there. Assuming you can find a static build of bash, we can just reference it like this /bash. The Nix evaluator will copy it into the Nix store and replace it with this hash. And this hash comes from, in this case, actually -sh is probably wrong. It should probably be -bash.
I was wondering, yeah.
Good point. Yeah, I didn't realize that. Yeah, but the point is that Nix will compute this hash for us because we said /hash. And as long as that file stays the same, it will always resolve to the same store object. It will not re-upload it again and again.
There is this name /bash defined.
Where is the name? Well, in the Nix program. So in the Nix program that we wrote, we said, in fact, I can show you. I think it's like in hello, no, it's just in hello. Yeah, you see there, bash is a file that I just have in that folder. And if we look at the, yeah, we're not very good on time, are we? Yeah, so we can reference that bash with /bash, and that's how it works. So let's speed through this. So it also computed the output hash for us based on the input hashes, right, which I mentioned before. So all of the hashes are computed for us. The system we had to specify with this built-in current system, and that's where this x86 Linux comes from. And the arguments were just passed as they are, right? So hopefully now you know what the Nix language, like what makes the Nix language appropriate for building these derivations, or more suited. Why is this not? Oh, that's not good. here. So hopefully that answers the question, what makes Nix the language appropriate for building these derivations. So this /bash, right, the one that we have copied in, there's no reason for this to be bash. It can be some other binary such as GCC, the C compiler, right? If we get our hands on a static build of the C compiler that doesn't have any dependencies, we can just feed it in to as the builder. So now this GCC gets copied into this builder and it becomes, sorry, into the input source, and then it becomes the builder. Then here's an interesting one. We can say, so GCC, the way it works is it takes a C file and produces the kind of an object file, right? So the C file also comes from our current directory, right? Gets copied into the Nix store as a store object. And then the hash of that store object gets computed. And then the argument actually contains the store path, you see? The hashed path to the hello.c. And in this way, we can use Nix to build a C project with this GCC.
Now so this .gcc is actually a binary block. It didn't recursively somehow build that. It is verbatim copied into the store.
So this ./gcc means this is a file in our current directory. We have to have a copy of the GCC. The Nix store doesn't know what GCC is. It doesn't know what bash is. It doesn't know anything. It's empty at the beginning. So we have to populate the leaves of our DAG with these programs. There's no magical bootstrap going on. We'll get to that later if we have time. So if we know how to build a C program, then we can write a little bash for loop that iterates through a list of C files and builds all of them, right? Has anyone built C before? Usually with a make file or, okay, a few. Yeah, so the way C works is you have a list of C files other than main.c usually. You build all of the C files into a .o object, right? And then you link them all together with the, actually you do build main.c as well into main.o, but then you link them all together, right? And you use the same binary GCC for both of these processes. So let's have a quick look at how this program works. We have a source directory, which we reference as /dot, that's standard. We take the GCC binary again with /gcc, and then we write a bash for loop for C in all C sources. GCC, take the source file and compute the .o file. And then we have the linking step, which says, take all the O files and produce the output file. We use built-ins to file to create a file called builder.sh. It can be named whatever. This file will be put into the Nix store and used as a dependency to our, in our derivation. Do I have a derivation file? No. Well, I stopped showing you the ugly JSON, but the point is that this builder.sh will exist as a bash file or as a shell file in the Nix store, and our builder, which in this case is once again bash, will take this file as its argument, right? Because we say args equals build script. So we will call bash with this script. Oh, and this script, I at least have that in the slides. This script, Nix will evaluate src and gcc into their respective store paths, into their pointers in memory, so to speak. And then the for loop stays exactly the same. Any questions about C building? Yes?
Where did mkdir come from?
The question is, where did mkdir come from? Where do we have mkdir?
At the top of the resulting script.
That is a very good question. I must have, yeah, I am in fact not entirely sure where that mkdir came from. I must have omitted it from the, good point, I'll fix the slides. Yes. So, yeah, another question?
There is a 10-minute break, which I'm obligated to give the students at some point.
So what I would suggest is that we get to the intermezzo, which there is, and then we have the break, and then I'll rush through the practical stuff. Okay, so we now learned how to build a C project. How exciting, right? Well, it is exciting, because many real-world projects are built with C, and they're built in the same way, sort of, right? There's some standard utilities, such as bash, GCC we mentioned, make is a tool probably a lot of us, or most of us here are familiar with. There's some other standard utilities like sed and so on. All of these are C projects. And if we build all of these tools, then they sort of recursively depend on each other, or kind of, let's say sed is probably built with make. Hopefully make doesn't use sed. But the point is, if we build all of these, then we can build anything that depends on them, right? It's a ever-growing tree of dependencies. So if we built all of these standard tools that all of these big projects, I mean, the Python interpreter itself is some sort of C program, right? So if we build up all of the dependencies, all of the C dependencies, we can then create a function that contains all of them and is able to build anything, right? Or at least a C project. And we can use this as a template for any C project if we then take parameters into this function. Let's have a real world example. So I will not show you how make is built, but I showed you that we can write a for loop that goes over C files, and you can imagine that a for loop that goes over C files, compiles them, and then links them can build a project like make, the GNU make, right? So we just pretend that there's a build make.nix somewhere in the somewhere on our file in our folder, and we can reference it with this import. And then we have another derivation that uses make, that puts make into the path environment variable. In Linux, anything you put in the path environment variable becomes accessible as a command like this. Basically, if we run the make command like this, it references the make that came out of this path. And now we can, here it should probably say make build instead of just make. So this function that we have here can build any make project. So any project that has a make file, assuming it doesn't have any other dependencies. Yes? And we can extend this further. So now that we know how to build a make project, we can use make to build something like glibc, which is a very, very common C dependency of many projects. We take our make build, we take our glibc build, which depends on make. This is some special syntax, inherit make. It's just make equals make. We pass it in as a parameter. And then we have a new function called mk derivation, a strange name, but it'll become clear in a second, where we once again populate path. We put make in the path. glibc is a library, not a binary, so we don't put it into path. We put it into something called ld library path. And then we, for some reason, decided to name the parameter build inputs, where we put glibc as an input to our mk derivation. The point is that we can put both make, which is a program, and glibc, which is a library, into this nix program as dependencies. One as a binary dependency that builds stuff, and one as a library dependency that gets linked against stuff. Okay, this is starting to become a template for, as I said, any Platonic C project, right? This problem has been, so this is how you can build it up, and this problem has long ago been solved, almost 20 years ago. In the repository called Nix packages. So Nix, the language, originally this was the way things were built up. And then once the problem of how to build make and glibc and so on was solved, all these files became public in this repository called Nix packages, so that we can reuse them. And how does that work? If we have Nix, this is again a Nix program, we can use these angle brackets to import Nix packages as a dependency. I will not go into how that works. And then when we have packages as a variable, we can use the standard C environments, the denv. And inside of there exists this function called mk derivation. That's why we called it this. And we just give it some parameters. We tell it the name and the version of the project we're building. We point it to the source files. It knows how to build make projects by default. So in fact, this build phase and install phase are optional. I could have simply dropped them. I don't even know why I put them in. But this function will build, and we even tell it the license. How nice is that? So that we can track if we're using licenses correctly. And this will build a make project with some of the, so it has bash, make, sed, all of those things that I listed before already wired in. In Nix packages, this MK derivation follows a pipeline. It's kind of how a Platonic software project is built in any programming language. It doesn't matter if it's C or Java or Python or Haskell. Usually, we fetch the source. We use some HTTP resource, GitHub, whatever, to download it, right? Then if we download a zip file or a tarball, we unpack it, right? That's the unpack phase. So these things happen one after the other, right? We can also skip them. So for example, if you just downloaded sources as source files, we don't have to unpack them. Famously, a lot of software in the world is not written with Nix in mind. So sometimes we have to tweak the sources a little bit to make them more, make them behave nicer in the sandbox. This is called patching the sources, right? Or maybe there's a bug in there that the software author has not yet fixed, but we want to fix for ourselves so we can patch the source before we build it. So in the C world, there's a configuration step usually where we detect all of the dependencies and the set of flags we use to build and so on. Then we perform the actual build. There's a check phase where tests are run. So there's no standard, maybe it calls make test. I don't think there's any standard for tests in C, but there is, for example, in Haskell. So if we have tests defined for our program, it'll just run them as part of the build. There's this install phase, which has nothing to do with installing stuff on your computer. It just means it copies the build artifacts to the out directory so they can be used later. And the fix-up is usually, again, if the software has created any files that are misbehaved in the Nix sense, like they have /bin/ whatever, it fixes those strings. It's just a little detail. So Nix packages is, as I mentioned, a GitHub repository containing a large amount of code written in Nix. It's entirely human written. Well, maybe these days there's some AI. But it has a community of tens of thousands of contributors working on it every day. It's a curated set of software. It's kind of the answer to the question of how can we build all software in the world with Nix. And all of this software in the world, quote unquote, builds together. So for example, if we change how we build make in Nix packages, this changes how we build everything that builds with make, right? So it's kind of a coherent set. All of the dependencies are used among each other. In Nix packages, we can have multiple versions of the same thing. So as I mentioned before, Blender 4 and 5, or Godot, right, recently bumped a version. So if it's important for people to have multiple versions, it is possible to build multiple versions of the same thing. An important feature of Nix packages is that when we download sources to some software project, they are cached, right? And then because the sources themselves are a Nix store object, they are reused between builds. Many packages in Nix packages have sources that no longer exist. So in a sense, Nix packages is an archive of all the software that has been, at least known to Nix packages. So if Nix packages ever disappears, quite a lot of software will disappear completely from the face of the world. And updating, so for a lot of the sources, a lot of the packages in Nix packages are still being actively developed. And those packages can be updated in an automated sense. There are various bots that crawl the Nix packages tree and try to update packages. And in this way, Nix packages is quite big and quite up to date. There's this website called Repology, which compares the sizes of various Linux package sets between each other. So the horizontal axis is the number of packages available. The vertical axis is how up to date these packages are. So this website, this graph in particular, is often used to tease Linux users, especially if you're using one distribution and you want to show your superiority to users of other distributions. This is the graph you would use. I'm sure Arch is somewhere up there and so on, right? So where do you think Nix packages is on this graph? Since I just said it's very large, it's very up to date, it's actually off the chart. This is a zoomed in version of that chart. So all of the normal Linux distributions, all of the basic ones are down there, and Nix packages is up there. In fact, those are various stable releases of Nix packages. And this is already a year old, so probably the next one is even literally off the charts. So Nix packages is very big, very up to date. It contains all of the packages you might possibly need, and if it's missing something, please add it. All of these packages, they come together to create something called NixOS. This is the last slide before the break, or the last topic. What's the point of NixOS? Why does NixOS exist? It so happens, so until now, we've been talking about how to build software dependencies. How do we make sure that when we're building a package, it has all of the things it needs to build? But what about when you run it? It so happens that some programs, when you run them, have runtime dependencies. If it's a server product, it might require a connection to a database, right? If it's a user-facing application, usually there's a configuration file that has to be there, or some such, right? Yeah, configuration files, as I mentioned, databases. Oh, yeah, right, there might be a dependency on some hardware device, like network. So the question is, this is more for, let's say, corporate deployments and whatnot. How can we make sure that when we put a program on a server and we run it, it actually runs and doesn't crash immediately because one of these dependencies is not met? How can we make sure that the server meets our expectations? Well, you know, this is Nix. The way we do it is we throw away all of the imperative stuff and we replace it with a declarative, principled way to construct the whole environment such that it meets our expectations. That's NixOS in a nutshell. NixOS is really just a Nix build, a Nix package, which brings together all of the various files that then pretend to be an operating system, such as the bootloader, kernel, and yada, 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 right? All of the files that you need to collect to make a computer boot. All of these components have multiple choices. For example, there's multiple kernel versions. There's, I think, 3 big bootloaders, and so on. Init processes are an eternal water cooler topic. So how can we make sure that if you pick and choose some of these components, it all still works? And in the NixOS, the way NixOS is built is it exposes these decisions as constraints, and then uses constraint solving to find the minimal solution that satisfies all of the constraints. Another way to call this is an expert system, which you might be familiar with. So we basically tell it what properties we want the system to have, and then NixOS figures out how to deliver on these promises. So the NixOS, the way this is done is with a novel pattern called the module system. And the Nix modules are a domain-specific language that are embedded in the Nix language. So it's not like you have to learn a new language. It's just a certain way of writing the Nix code. It allows you to have independent declarations of facts. It allows you to state, I don't know, my computer uses an NVIDIA graphics card. My computer has a SSD of this size and so on. And then it brings them all together and builds a big data structure. Right, yeah, we'll get onto that data structure later. Yeah, these options, these facts can be declared and defined separately. So there exists a file that contains all of the, or several files that contain all of the possible things you can specify about your system, and you can also add your own declarations. And then you define these things separately. You can define them multiple times, in which case something like merging happens. The module system has a type system. I mentioned earlier that the Nix language is dynamically typed. Module values can have types that constrain what's possible. The type system also defines how it deals with conflicting declarations. You can have 2 files in which one says, I have an NVIDIA graphics card, and the other file says, I have an AMD graphics card. The module type system then decides if this is an error, or if it's valid for a system to have both, right? Both an NVIDIA and an AMD graphics card. Sometimes it's merged, sometimes it's a conflict. Yes, I'll skip the fixed point computation stuff. In functional programming, we can use fixed points so that the whole of a value can depend on some parts of the value. Yeah, I have an example of what modules look like. I'll rush through it in the name of saving time. So when we evaluate all of the modules together, we get a data structure, which I mentioned before, which is the entire configuration for an operating system. And this is what an example of this looks like. Do we have the NVIDIA graphics card somewhere? Yeah, down here. It says video drivers equals NVIDIA. We can open firewall ports by listing them as such. Yeah, so this is what an example of what a NixOS configuration looks like in the Nix language. Any questions? Question?
I have a question. So it's not just configuration files normally, but it's also how would Nix handle something like logins or passwords that I need for an external service? I don't know, my OneDrive or something like that.
So the question is, how does Nix handle things like passwords or credentials for external services? Well, it depends on what you're configuring. If you're configuring a client, which is then part of your operating system, that client probably has a configuration file. You have multiple options. You can choose to put an encrypted file into your Nix store and then just reference that. Or you can just leave it completely undeclared and just do it kind of imperatively in a stateful way. Obviously, if you want to declare everything for a server, for example, then you want to do it the first way, which is with the configuration files as part of the NixOS config. But it is possible. Basically, every client, everything that has a configuration file, you can put its configuration file there for it, right? You don't have.
It would have to have a text configuration file.
Yeah, it would have to have a configuration file, or alternatively, if it has a data, so sometimes a service that you're running on a server has its configuration in a database. And maybe it doesn't expose a way to declaratively initialize it. What you can do is you can declare a system startup service that when the system boots, but before this service runs, connects to the database, populates the database with some fields in some table, and then when the service starts, it already has a populated table. So it's always, as long as you can write code that can create files on or resources on your machine that will make something initialized, you can always do it with Nixos.
Got it. Thanks.
So everything can be declarative if you put enough effort into it. Yes, question?
Or, for example, you could wrap the binary that accepts some arguments with the credentials file or the credentials just for standard input, then you could wrap that with the script.
Correct, yeah. So another way to make stuff declarative for Nix is you can take the binary of this program and make a wrapper, like a bash wrapper around it, which either asks you for these things or kind of takes it from some environment, or even just has them baked in. Although in that case, you're exposing plain text credentials. Any other questions about NixOS or any of the other stuff we talked about? OK, in that case, I suggest we take a break.
Yeah. So the break will be 10 minutes. It's 17 now. We come back at 27. Okay?
If people want to follow along with the practical stuff, I put instructions on how to install Nix and enable a feature called Flakes up here. It would, if you have a laptop running Linux, you can just follow these steps. Actually, I think it works for Windows as well.
I guess there's not enough time to install NixOS on the laptop in these 10 minutes, right?
Yeah, but this is just the Nix binary.
Yeah, yeah.
So the question is, if the assumption is that you always have this bash and GCC binaries present on your machine, or if they are bootstrapped in some way. So before we talked about Nix packages, we constantly referred to these bash and GCC because they have to come from somewhere. If you use Nix packages, then the bootstrap has been done for you. And you can use, let me scroll back. It's going to be quite some scrolling. You can use that MK derivation function. So basically, if you don't use Nix packages, then you have to do it that way. But if you use Nix packages, you can just use this. And you don't have to deal with make and bash yourself. It's all wired in for you. That's the point. Does that answer your question? Before the Nix packages topic, I was showing you how the very first packages in Nix packages were created. It's an interesting, if you talk to people who know Nix, usually the first thing they do is they do this first line, import Nix packages, and then they start using Nix packages initially. In fact, Nix's own creator, Eelco Dolstra, who has a PhD in this stuff, thinks that Nix and Nix packages are completely inseparable. You can't meaningfully use Nix without Nix packages. But I don't think that's true, because you can always ask yourself, how was the first package in Nix packages created? And most people who learned it through Nix packages might not actually know that. But after following that C building torturous example, you now know how that works. So you always need to bootstrap. You always need a binary at the beginning. But this is many, many layers of abstraction. This standard environment, Student, has this bootstrapping done for you. OK?
But then this initial starting point that you bootstrap off of is not declared in Nix. So it's sort of like the poison source. You don't know how it's created. You just trust it and assume I can execute it.
Yeah, that's a very, very good point, yes. So the bootstrap process, it's like probably deep down there's a binary blob somewhere that Nix packages itself uses. I mean, this is the bootstrap problem. There are some other research projects like GUIX, which is a fork of Nix, and they have their own community by FSF, or by GNU, basically. They have solved the bootstrap problem in some way, but I haven't studied it. So if you're curious about that, it's a very, very important topic. It's actively researched in Nix, and as I understand, GUIX also has a solution for it already. The problem of how do you not trust binary blobs to start your environment, right? But we definitely need people like you in the project to help us figure this stuff out. Yeah, now I lost my place. OK, there we are. So assuming you all installed Nix, I have to give you a warning that the stuff we're about to look at, the flake features, are technically still experimental, which means that they're still under active development. Some small implementation details of them may change. But I gave this lecture a year ago, and nothing has changed. So we're good. OK, let me teach you some magic tricks. I don't have any sleeves, so there's nothing up my sleeves. Let's look at the CLI, so the command line interface of Nix. It allows us to do some nifty things. OK, is anyone following along? Does anyone have Git installed on their computer? If you run git -- version, do you get this? Hopefully. If you don't, then how do you do your schoolwork? Does it work? It works? OK, I guess it works. Let's try this one, fortune, like run the fortune command. Did you get your fortune, or did you get command not found? You got command not found? OK, good. If you installed Nix, you can now use Nix run Nix packages #fortune. So it's like out of Nix packages, pull the fortune package. And if you do that, you'll get a fortune without ever installing fortune. All you have to install is Nix. And if you then run the fortune command again, it's still not there. This didn't actually install it. It just whispered fortune onto your hard drive. We can play with this further, right? We can use fortune as well as a very important program called cowsay to have the cow tell us our fortune, right? Without installing anything but Nix, right? In fact, we can enter a shell. So we use Nix run until now, right? We can enter a shell with Nix shell, which has these two very important programs available. Then we enter another kind of a subshell, And if in this subshell we run fortune causa, we get another fortune. And then we have to exit out of this subshell, or Control D, to get back to our normal terminal, in which we once again don't have fortune or causa. There's a very nifty trick that I like to teach people with these curly braces. Most people don't know this. I don't know why. You know how we used nix packages hash fortune, nix packages hash causa? We can extract this common prefix and use these curly braces to specify 3 things that come after hashes: fortune causa and lolcat. Very important. And then we get a colorful fortune set by a cow. Okay, so I hope you're getting the gist of it. You can use nix to run anything at all without installing it. Right. However, using these nix shells, kind of running these commands over and over again, it's just as error prone as kind of having to install stuff, right? So what we're really interested in is how can we save us, like how can we declare that we depend on fortune causa and lolcat, very important for our project work, in a file so that this file can then persist. And there's 3 common files that exist in Nix projects or Nix powered projects. Flake.nix, which is the one we'll be looking at today, or default.nix and or shell.nix. It's basically one tells Nix how to build it, one tells Nix how to allow us to develop it. For now, we'll focus on flake.nix, which does everything, and the rest we can ignore. And what's cool about Nix is that if you have a project, let's say in Java or Python or Haskell, you don't have to change any of the source files. Okay, maybe the make file if you wrote it in an opinionated way. But the point is that a Haskell project or a Java project with Nix is still just a normal Java project. It just has a file added to it, which we can then throw in the trash if we don't like it. That's the promise of Nix. So I'm going to walk you through how to write a flake. I'll speed through it because we don't have that much time. So remember, a flake is a file called flake.nix, which is at the root of the project. So if you're using Git, it's where your .git folder exists, or .gitignore or whatever, right? Okay, a flake is a Nix file, which means that all of this is a Nix syntax. This is a Nix program. It has these curly braces, which makes it an attribute set. It has a certain schema, so a certain shape of flake is expected, inputs and outputs. Inputs declares resources that we will depend on that are not present in our current project. If you wrote a Java project, you have some .java files in your folder. What you don't have in that folder is the Java compiler, or do you? You know, hopefully you don't. So where does this Java compiler come from? Well, you installed it, and now it's in /bin/javac. Well, with Nix, you can declare a dependency on, in this case, Nix packages. So this is some special syntax that says from the GitHub repository Nix packages at the tag 2511, we pull this entire set, this entire universe of Nix packages, which also contains our C or Java or whatever compiler. There exists a shorthand for this, which I won't spend too much time explaining. Then in the outputs of the flake, we can refer to the inputs. So these inputs are the same. And then we return an attribute set out of outputs. This is just hello world. Once we have a flake like this, we can use a command called nix flake show. And it will tell us that we have a hello attribute here. Yeah, this hello is here. And in fact, we can evaluate hello. This is dot is the current directory, hash is out of, right? So out of the current directory, evaluate the output named hello, and it's a world. That's how we defined it. Okay, let's do something more useful. Let's use these Nix packages and take packages out of it. Nix packages is a set of packages for many systems, Linux, Mac OS, no Windows yet, but we're getting there. So we have to declare which package set we're interested in. My computer is an x86-64 Linux. Maybe you have a Darwin or such. There's some other examples on there. So given this system that we declare, we can import Nix packages. So Nix packages, the input is just the sources, and we can now import the sources given the system to get out the packages set, which is this packages equals. And now we can start using this packages set. So this dev_shells.system.default is part of that schema I mentioned before. So the outputs of a flake have to have a certain shape. It so happens that if you have an output with the name dev_shells.x86-64 Linux, or Darwin if you have Darwin, .default, that will be the kind of the development shell of your project. We'll see examples of this later. And then we can use finally this packages dot, which is this variable that we declared there, mk shell. to create a dev shell, development shell. And into this shell, we can then finally put our very important fortune cow say lolcat as a list of packages that are kind of dependencies of this shell. And there's another little syntax sugar that we can say with packages to drop the packages prefix. All of these examples are in that GitHub repository that these slides live in as well. So now that we've created this Flake file, we can use a command called nix develop to enter a development shell in which we have fortune, cow say, lolcat, and so on. If it has a shell.nix, it's a different command. So if we write this Flake, we run nix develop, and then fortune, cow say, lolcat, we get a colorful cow. OK. Another important feature of Nix Flakes is that the input gets locked, just like if you use the JavaScript, npm creates a lock file. I won't spend too much time on this. Basically, it means that if we evaluate the same project again some time later, we get the exact same resources hashed with a cryptographic hash to make sure that nothing has changed, assuming that they are still available behind the URL. So in the case of GitHub, as long as the GitHub repository can be cloned, we will get the exact same snapshot of the project, which is an important property of reproducibility. Yeah, so Nix will create a flake.lock file the first time we use, we just wrote a flake.nix. When we use flake develop, for example, this lock file will be written, which contains hashes and timestamps and whatnot. OK, let's look at something useful. We have a C project, which prints hello world. Very important. How do we build such a C project? We need the C compiler, right? So I mentioned earlier that there's this student MK derivation that already knows how to build C projects. So this is our Flake, right? We have the same inputs. We have the same outputs, system, packages, whatever. And instead of dev shell system default, now we put packages system default, which is another special name for the package that we are building. And if we nix build, what's the problem here? Right, so I promised that Nix already knows how to build C projects. The problem is that C projects, like just a main.c file is not enough for a project to really understand what it means to build or to install it. Traditionally in C, you would use a makefile. So in a makefile, if you additionally have a makefile, which contains build, hello, how to use CC, and then install, this step is important, this install, which tells Nix, or traditionally in Unix systems, it tells you how to take the build files and put them into /user/bin or whatever, right? In the Nix mk derivation function expects to be able to install stuff using make install. So if we add this file, this exact file, and then we run nix build, it builds successfully, it says nothing. And then if we run it, we get our hello world, right? So two files, main.c and makefile and mk derivation, and off we go. Let's make the C project a little bit more interesting. So last year I had an example with TensorFlow. Since then, TensorFlow has been abandoned apparently. So this year we have Lua. Lua is this interpreted language. It's invented to be embedded into languages such as C. So we can write the C program that embeds Lua and then runs this print hello from Lua Lua program, really, right? It evaluates it. And the only thing we have to change in our makefile is to do this -l Lua. This is the link, like link against Lua command. So this is how a generic, like this is how our previous Nix expression looked to build a C project. We will need to add a single line of code to it, build inputs. So we tell it that to build this project, we also need to take Lua out of packages. So in addition to the standard environment, Lua as a library is needed to build this project. Oh yeah, and if we have a dev shell, we also should then add Lua as a dependency of the dev shell so that if we run GCC manually or make manually in the dev shell, it doesn't complain that it can't find Lua. So if we run this project after we've added Lua, we get hello from Lua. How cool is that? With no Lua installation required, just a single line of Nix. OK, let's look at Python. In Python, you want to do ML, to get with the times. And the current get with the times is PyTorch, I think. So if we import PyTorch in Python, and then we try to use it, Normally, you would have to create a devenv, or I don't know what Python people do. But the point is, you don't just have Torch already installed in your system. But you can put Python 3 with packages ps torch into your dev shell. And then if you nix develop, OK, this is just shorthand for nix develop. And then in the subshell, you write Python hello.py. Hello.py, by the way, contains this, right? We get our PyTorch in there with no Python nonsense devenvs required. OK, question?
Side note, if you have a Python project and want to use it with other people that use Python but not Nix, you could, and if you like abstractions, then you can use UV to Nix or PyProject.Nix to be able to read the dependencies from the PyProject or from the UV.
Correct, very good point. Yes, this actually, I have an example of that with Haskell. It is possible to read Python's own dependencies format and kind of automatically wire them in. So you don't have to specify them both in, what was it called again, UV?
I think PyProject.toml is the...
Yeah, there's various project description languages that various programming languages use. In Java, it's like this Maven XML file, right? pom.xml, I think it's called. In various programming languages, these specifications already exist. And in some cases, Nix knows how to read them. We have an example with Haskell later. So, remember earlier how I said that Python is, when I said that Docker is terrible and Nix is amazing? Well, remember, Nix can build anything, or Nix can have a pipeline that builds anything. It can build an operating system, so why couldn't it build an OCI image, a Docker image, right? An OCI image, as I mentioned, is just a binary blob. So if Nix knows how to build a piece of software and kind of collect all of its dependencies, theoretically, or quite realistically, it can take all of these dependencies, all of these binaries, and just put them in a binary blob. And then we have a binary blob that Docker can use, right? So for this, I have a little Haskell example now. This is the world's smallest Haskell, well, it's not a hello world, but it's like a web-powered hello world. On the left is a Cabal file. This is this dependency specification language that Haskell uses called Cabal. We say we depend on base, HTTP type, Y, warp, some web server stuff. On the right, this is the entire Haskell program. It just creates a web server that says hello Haskell when you get / on this server. So the left one is a hello.cabal. The right one is a main.hs. Yeah, correct. And here's how we can build a Haskell project with Nix. So most of this is just boilerplate, right? So inputs stays the same. Outputs, system, packages, import, blah, blah, blah. This is all the same, right? Now we have a package system default, which calls, instead of studenv mk derivation, it calls Haskell packages.call cabal to Nix. This is the magical incantation that will build a Haskell project with Nix packages. And we give it the name of the project, blah, blah. Right, what we can also do is we can take this line here, we can give it a name called hello, let hello equals that, and then just reference it here. You can always do this in a functional language, right? Take a subexpression, give it a name, reference it by name. So if we now Nix build or Nix run, let me tell you a little secret. Nix run just calls Nix build and then calls the result /bin / the name of the package and runs that. So Nix run will build this Haskell project and run the main module, right? So I don't have enough time to real-time demo this for you, but if I run it and then in a separate terminal I access localhost on port 3000, which is what it listens to, we get hello Haskell. Without any dependencies, without anything. Okay, remember what I said, when you Nix build this, you get a /bin / hello, right? This is an executable. We can use a Unix command called LDD to look at the runtime dependencies of this binary. There's quite a few. So if we wanted to build a Docker image with this binary, we would copy the binary into it, and then we would have to make sure that all of these various libraries are also installed with apt install lib lzma, whatever. And that hopefully, we don't have to match the versions, but sometimes also the versions are tricky. So, and it sure would be a shame if we forgot any of that, because Docker is not going to tell us that. We only have to test it ourselves, right? That's the only option we have. Well, with Nix, what we do is if we already have a let hello equals how to build this, let's have an image. Let image equals build layered image. We can also just build image, but layered image is cooler. So we can use Docker tools within Nix packages to build a Docker image. We have to give it some name. Aha, here we say that the contents of this image is the hello. It's this hello here, right? You see, it's not a packages.hello, it's just this hello. And what this will do is, remember Nix does this whole dependency tracking thing, right? This will put into the contents of the Docker file the hello binary, as well as all of the runtime dependencies it has, and all of the runtime dependencies those dependencies have, right? It's called a transitive closure. We have to tell it how to, the entry point, I think it's called, the program that will run when the Docker image is executed. That's the, we don't even have to hard code it as hello. We can take the meta main program thingy. And then we just expose it as a packages.image, you see? And if we now do Nix build image, and we look at what came out, so every time we do a Nix build, it creates a result link in our current directory. And then if we look at this result, we see that it's this hello, like hash hello tar gz. What this is this binary blob that I told you about. And we can see it's, oh, we can't see that here, but it's, I think, 20 megabytes big, which is really very little. If you've ever used Docker images, it's like hundreds of megabytes. But Nix builds very, very efficient ones. Then we can use Podman or Docker, if you're still using that, to load this file. And then after it's loaded, we can run it as such. And then it works through Docker. I don't have time to demo it for you, so just trust me, bro. Any questions about Docker so far? OK, last topic. Nixos tests. I promised that I would show Nixos tests. So we know how to build Docker. Cool, Docker also knows how to build Docker. But what Docker can't do is run tests. At least it's not like built into the basic thing. Nixos, or yeah, Nix with the powers of Nixos allows us to specify.
So let me just say something before continuing. This is a guest lecture, right? If anyone's interested in continuing, we'll all be here. If you're not, feel free to leave, have lunch or whatever. Right? After this, this will not include the syllabus for the exam, right? This is a joke. There is no exam. Right? So you're free to leave.
What do you mean there is no exam? I will quiz them on their way out. I literally need 2 minutes for this.
Yeah. So take your time. Don't worry. Don't rush through it. Anyone wants to leave, just leave. It's cool. Feel free to continue as long as you want.
No one left. OK. All right. Let me tell you really quickly about Nixos tests. Because Nix knows how to build an operating system, Nix also knows how to build a VM image, like a virtual machine, right? And if we know how to build a virtual machine, we can create a network of virtual machines that can talk to each other. And those virtual machines can run any program we want. So how is that possibly useful, right? We can test a client-server topology. We can have a server, which we just wrote, this hello server, and our test can be an integration test that says if we start this server, a client can talk to it and get an unexpected response, right? So an integration test that creates virtual machines. So this is our Haskell project built with Nix, same as before. All we have to do is add a checks. This is, again, part of the schema, checks.system. And then this is just a name, can be whatever. I call it Nixos test. And then we use packages testers Nixos test to declare a Nixos test. I'm just going to zoom in on this attribute set here so we don't have so much noise on the slide. So here are the parameters we give it. A name, a specification of nodes. So what are the actors in this network? A server and a client, presumably, and a test script. Let's zoom in on the nodes. As I mentioned, server, client. These attribute sets here, this nodes server equals this, is a Nixos configuration. So in the same way that you configure your computer, you can configure these virtual machines that run in this test. So we say that the firewall of the server has to have port 3000 opened, right? We create a very, very small systemd service to launch our server at startup. This is this multi-user target systemd thingy. We tell it to run hello at startup. And that's it. That's all we need for the server to launch hello at startup and to have port 3000 open. The client, on the other hand, needs curl to talk to the server. Can be something else as well. Could be Firefox. And now all that's missing is the test script. Let's look at the test script. The way Nixos tests works is it has a Python library that allows us to write a script in Python. So this here is valid Python code, which then allows us to interact with these machines. So what do? We start machines. On the so the server dot, it's this object-oriented pattern. On the server, we wait for port 3000 to become opened. And then we have an expected string called hello Haskell and an actual string which comes from running the command curl HTTP server 3000 on the client. So the client executes curl to talk to the server, gets back a response, and this is our actual string, and then we assert that expected is the same as actual. That's it. That's the whole test. Any questions? So how does this work? If we build checks.x, this is my current system, .nixos test, right? If we build this output, we get tons and tons of virtual output. I don't have time to show you. It basically boots up both of the virtual machines, and then nothing more. And if we look at the output of that execution, it's 0. But also, if we read the build logs, which is what print build logs does, it says succeeded. It's green, check marks, all is well. And it takes, I think, 3 minutes to run 2 virtual machines and execute this test, at least on my laptop. And that's all, as I promised, 2 minutes. Thank you very much for your attention. I just want to tell you about this meetup that we have. So this is the website, zurich.nix.ug, which stands for user group, apparently. We run twice per year. We run a hackathon right here at OST, so far, by the grace of OST. And you can follow us on this website or on the meetup webpage. And we have a Matrix channel if you want to chat with us. And now that's really it. Thank you.
Thank you very much, Alex. Are you still taking questions? Does anyone have any questions?
OK, now it's on. Sorry. Yeah, the question was, how do you select the correct package to supply some dependency? So a nice example of this is, let's say, LaTeX, right? Like you have a .tex file you want to build with some LaTeX compiler, probably PDF, what is it, TechLive, right, is a Linux package for that. How do you just know that? Well, there exists a really cool website, which I can't show you because I don't have internet access, called search.nixos.org. Which allows you to put certain things into a search box and it'll list you the packages. Question?
But there are like so many that then take live and then full and combined.
Yeah, there are many. LaTeX is a good example because there's many flavors of TechLive. There's TechLive full, TechLive small, and so on. You just try, I guess. You try a few. So I have an example in this repository of a LaTeX project where I use TechLive small, because I don't want people to download for I don't know how many gigabytes of tech just to build a hello world, right? It depends on what you need. For many packages, it's very simple. For example, for Python, do you want Python 3 or Python 2? Probably doesn't even exist. There's also Python 3.1.1, 3.1.2, 3.1.3, right? So usually you know what you need. But sometimes you don't know which package supplies a certain library or a binary. For example, I don't know, unbuffer. The unbuffer command comes from a package called expect, which I happen to know. There is a project called Nix index, I think it's called, which allows you to query. You can ask it which package provides a file called /bin/unbuffer, and this I can show you because that doesn't require an internet access. Nix locate /bin/unbuffer, I said. Expect, there it is. You see? We can also do a library. Let's say lua dot, I don't know, so. And there's the various luas. So again, you have to ask yourself which version of Lua you want, but hopefully this one you can figure out yourself. But yeah, search.nixos.org and Nix locate or Nix index or whatever it's called. Let's actually ask it. No. It's Nix index. Okay, any other questions? Yeah?
So I'm an upstream of an open source project which is packaged in Nix. And I see there are a couple of patches there for example, if I'm assuming something is in /usr, that will not be true for Nix. How is the interaction there between NixOS and upstreams? Like, would it be better if I read some Nix-specific environment variable and use that?
Excellent question. The question is, if we have a piece of software that wasn't written with Nix in mind, which, how could they? What's kind of the idiomatic thing to do? And I want to show you something right here. You see this bin dir equals. So this is an idiom, a makefile idiom. It's not required because this name could be whatever you want. It just so happens that if you look at real world projects, they often use bin dir. And so Nix has learned to respect it and to use it, right? So if a programming language ecosystem has idiomatic ways to express that it should be in outbin or /user/bin or whatever, like with some variables or so on, then hopefully you can just, the way you would do it is that in the Nix file, here you would say something like env.out there or bin there equals something else, right? So you don't have to change the source. Everything can be done in Nix, right? Some programming language ecosystems or some programs are written in such an opinionated way. Sometimes they have /bin/bash in the scripts, like just hard-coded in, and Nix doesn't have access to that because it's in a sandbox. There are several ways to address this. You can use the patch phase to patch the source files. So there's a patch shebangs function, which replaces all bin bash to the Nix equivalent, just automatically for all of your sources. But some patches are more tricky than that. And there, Nix packages has the following rule. If the change to, or rule, guideline, if a change to the source tree is generally a good change in the sense of it makes it more general, doesn't hurt the upstream, but kind of helps them become more general, then you should open a pull request and then download the patch from this pull request in the Nix build. Either wait for it to get merged and then pull that version, right? Or patch the source with the patch generated by GitHub. If you look at the Nix package's source code, or we can look at it later if you want, you can find many examples of this, where the upstream has a pull request open that we need, but then we just reference that pull request while building, and it's all good.
Right. So I should probably just talk to the Nix maintainer of my package.
Yeah, so if you have a suggestion for improvement of a package, or if there's a patch that needs to be added, yeah, talking to the Nix maintainer is a good idea, but you can also just open a PR upstream, right?
I think his original question was the reverse. He is the upstream
Oh.
and wants to play nice with Nix. He sees that the package in Nix packages of his software has some patches and asks for, how can I make this?
Oh yeah, absolutely. In that case, the Nix maintainer, which should be listed, is the correct contact, yeah. Question?
So I have like a CLab package, and there is the manual is missing, so I can do main CLab. Do you know?
So CLang?
Yes. Do you know how to add the man pages for it?
The man pages of CLang to NixOS or what?
Yes. If I use it in
If you use it in the shell, I don't think you can get man pages because man pages have like our system level. There might be some way to access them. Actually, I think I can probably show you some. The question is a package like clang. If we nix, oh, I can't build stuff here because I don't have internet access right now. But if you nix build clang, like nix packages hash clang, and you look at its result folder, it will have a share. So somewhere in there will be the man pages. So you can probably use a pager program to access those, but I've never tried doing it that way. Let's see. Yeah, you see, there's man. Okay, and if you know how to use this, I'm not entirely sure, but I think there's a program that can read this. Okay? Question.
So there was a bit of a jump between everything else in Nix and then Flakes, right? Is Flakes just a convenience, or does it do something fundamentally different? How would the world look like in the last part of your lecture if we did use Flakes? Because it seems like it's something on top of Nix because it's not yet.
Very good question. So the question is these flakes that we looked at, this entire schema thing, right? How does this compare to Nix without flakes, which is vanilla Nix, if you will? How were things done before flakes? So the answer to that is that all of the schema, so inputs and outputs, and this packages system default equals, up to this equals with default equals, that's flakes. Everything after it, so packages.stdf.muck derivation, that's normal Nix. So if you don't use flakes, you basically erase everything except this packages mk derivation to the curly bracket. So then the question becomes, where do you put that? And the answer is you put that into a file called default.nix, which has a I have that one actually as well. I have one single example, which I of course don't mention. Actually, it's here. Yeah, this is what your default.nix might look like. So this is Nix without flakes. It imports packages from this angle brackets Nix packages, which is some environment scary stuff. You see, you don't specify where Nix packages comes from. You can, in truth, you can say here, fetch this git resource with this hash. You can do that. Just for brevity, I didn't do it here. And then you say packages dot, and basically the rest of the file, you see there's no semicolon here, is the return of this expression, which will result in this package. And then if you use nix dash build instead of nix space build, it will take the default.nix file, evaluate it, find Nix packages, and do everything. So the answer of what role do flakes play is that boilerplate that we removed is, it makes things explicit. Where exactly do Nix packages come from? What version are they? You can do all of that in vanilla Nix. The only difference is that flakes have a schema, so they have an expected shape. There's hopefully only one way to do it. There's only one way to specify which Nix packages you're using, only one way to specify which package you're building, right? And of course, a convenience is that you can have a development shell and the package build in the same file, or a Docker image in the same file. You know, you don't have to have multiple files for all of that stuff. And you can use let bindings to share things between them, which would be trickier with vanilla Nix. Because it's all, you're welcome.
Okay, I guess there are no more questions. Let's thank the speaker again. Thanks, Alex. Yeah, that brings us to the end of this semester, at least for SCP1. This